All right, I'm going to run through some quick solutions to the midterm practice problems. Number one, a person slides down a zip line tightly strung at 10 degrees. The line is 75 meters long. Find the speed at the end if they start at 1 meter per second. All right. So from the kinematics here, we don't have enough information. We need to find A, and we're going to do that with our forces. So this is identical to something on a ramp. So if we look at our forces, we have gravity, and we have a normal force holding the wheel on the zip line, and that's it. If we look at our components here, we're going to have normal forces in our y direction for our rotated y-axis. We'll get the normal force minus Fg cosine theta equal to 0. Remember that the y component here is cosine because the angle of incline is the same as the angle here between the vertical and the between the y-axis and the vertical. In the x direction, all we have is the x component of gravity, and that's equal to ma. The gravitational force is mg. So we can divide by m, right? And we get that A is equal to g sine theta. In this case, that would be 9.8 times sine 10, 1.7 meters per second squared. All right, so now we need to do the kinematics to figure out what the question was actually asking, right? Let's do that. All right, so in the kinematics, we're going 75 meters with V naught equal to 1. A is 1.7. And we're looking for V final. So I think here I'm going to use the V squared equals V naught squared plus 2A delta X. And we want V final, right? We got the initial, we got the acceleration, and we got X. So 1 squared plus 2 times 1.7 times 75, and take the square root. All right, so 2 times 1.7 times 75 plus 1. And you get 16 meters per second when you square root it. All right, number 2. A person is running at 5 meters per second. When they see they have 50 meters left until they get to the end of the track. If they start slowing down at a constant acceleration, what acceleration will have them come to a stop at the finish? So V final equals 0. All right, so this is just a straightforward kinematics equation. Same as the last one, just we have different values for our velocities. And it's the A we're looking for. So we have V squared equals V naught squared plus 2A delta X. The final velocity is 0. The initial velocity was 5. 2 times A times delta X was 50 meters. Doing our math here, minus 25 is equal to 100A. A is minus 1/4. And the units, of course, are meters per second squared. We can check that out with, this is meters per second squared, meters per second all squared, right? And then we divide by meters. So that checks. So minus 1/4 meter per second squared, or you could say 0.25. A dog drags itself across the floor with its front legs, right? So here's our dog languishing as it drags itself across the floor. If the dog is 7.5 kilograms and the force applied is 12 newtons, find the coefficient of friction between the dog and the floor. Okay, and here I had a missing thing in the typo I told you all in class. V is constant, is the assumption that we're making. Right. So with our free body diagram, we have the applied force of it dragging, we have the frictional force, we have the normal force, we have the gravitational force. All right, constant speed means A is 0. And we get balance in the X and Y direction. I'm going to skip the intermediate steps here since this is a trivial free body diagram here, right? The normal force minus gravity equals 0, so they're equal. The applied force minus friction equals 0, so they're equal. We know that the kinetic friction is equal to mu times the normal force. And we just said that the normal force is equal to the gravity in this case, which is mg. So friction equal to mu mg. So mu has to be equal to the frictional force divided by the normal force. And the frictional force we know is 12 newtons, right? Because it's equal to the applied force. So I guess I should make that substitution. So we have 12 newtons over 7.5 kilograms times 9.8 newtons per kilogram. We get that mu is 12 divided by 9.8 divided by 7.5, 0.16. No units on that, right? Because it's the ratio of two forces. Number 4. A small child pulls a teddy bear in a wagon. Here's our wagon with a teddy bear in it. The total mass is 5 kilograms. And the wagon is pulled at 20 degrees above the horizontal with a force of 25 newtons. Find the acceleration. All right, so A, do our free body diagram. We have gravity, we have our normal force, and we have our applied force. And the point of the wagon here is that it has wheels, so we're going to assume that there's not a lot of friction. All right, so if we look at our components now, the sum of forces in the y direction, we have the normal force plus the y component of the applied force minus the gravity equals 0. All right, because it's staying on the ground. And in the x direction, we just have the x component of the applied force equal to ma. All right, so if we look at the x component here, it is the adjacent side, so it's going to be the cosine. So we have f cosine theta is equal to ma. A is equal to 25 newtons cosine 20 divided by 5 kilograms. All right, so 5 times cosine 20 is 4.7 meters per second squared. All right, B. Draw a free body diagram of the bear and of the wagon. So if we look at the bear has gravity acting on it. It has a normal force due to the wagon. And what else is happening, right? So at this point, you have to imagine what would happen if there was no friction between the bear and the wagon. The wagon would just slide out from under the bear, right? So there's actually a force of friction in the positive x direction, which is what accelerates the bear. So now let's look at the wagon. If we look at the wagon, and let me, since we have two things, let me be real specific with my subscript here. This is on the bear due to the wagon. All right. Now for the wagon, what do we have? We have our applied force, which was at 20 degrees. We have the normal force on the wagon due to the earth, or the ground, let's say ground. And we have a normal force on the wagon due to the bear. And we have the force of gravity on the wagon. All right, what else? Well, we have this frictional force on the bear due to the wagon. So we must have a frictional force on the wagon due to the bear. And you can think about that again. The wagon is going to go slower because the bear's adding more weight to the whole system, right? So that frictional force opposes the motion, right? And I think what's tricky about this one is the frictional force on the bear, because it's actually what causes the motion of the bear, because the bear left to itself would just sit still. It opposes the intended motion, because if we have the bear sitting on the wagon and the wagon starts to move, then the relative motion of the bear would be to the left, right? All right. Part C says where are the interaction pairs? Well, we have the force of friction on the bear due to the wagon equal to minus the force of friction on the wagon due to the bear. And we have the normal force on the bear due to the wagon equal to minus the normal force on the wagon due to the bear. And that's it, right? That's the only interaction between the two objects. We could talk about the other ones for the gravitational forces. It would be the force of gravity on the earth due to those objects. For the normal force on the wagon from the ground, it would be the normal force on the ground due to the wagon. And for the applied force, it would have to be the force that the child pulls on the wagon, right? The wagon pulls back on the child. All right, so number 5. A light fixture hangs from 2 thin chains. One makes an angle of 30 degrees with the ceiling, the other 40. If it has a mass of 2 kilograms, find the tension in each chain. All right, so free body diagram on the light fixture. Got a force of gravity. attention due to this chain, attention due to this chain. What do we know? Well, if we look at our components, we'll have our X components, we'll have our Y components. Again here, assuming a standard coordinate system. Right, I really shouldn't draw my components before the coordinate system because the components have to be parallel to your axes. If we sum forces in the Y direction, we're going to get T1Y plus T2Y minus the gravity equals 0. Sum of forces in the X is going to be T2Y minus T1Y equals 0. Because the light fixture isn't moving, right? It's at rest, so our acceleration is 0. All right, so we need to, oops, I wrote Y's here instead of X's. Sorry, these are X's. So we need to do our trig. If we look at T2 and we look at T1, T2Y is going to be, what angle's on that side? The 30 degree. T2 sine 30. And T2x is going to be T2 cosine 30. I'd say the one thing to be careful with this type of problem is whether you're given the angle from the vertical or from the horizontal. Since we said it's to the ceiling on this, that means it's from the horizontal. So there's no trickiness in the trig. T1 sine 40 and T1 cosine 40 for T1x. All right, so now we can plug in everything. We've got T1 sine 40 plus T2 sine 30 equals mg. And we've got T1 cosine 40 equals T2 cosine 30. There are two equations. And now we just need to solve them, right? We've got two unknowns, T1 and T2. We know the mass, we know G. Two equations, two unknowns. Easiest way to solve here would be substitution, I think. So I'm going to solve equation 2 like this. T1 is equal to T2 times cosine 30 over cosine 40. So we can plug that in right now and see what that coefficient is. Cosine 30 divided by cosine 40 would be 1.13 times T2. All right. So now we can plug that in for T2 in the other equation. Or sorry, for T1 in the other equation. So 1.13 T2 sine 40 plus T2 sine 30 is equal to mg, which is 19.6 because it was 2 kilograms. So now we just need to do our trig. 1.13 sine 40. So this will be 0.726 T2 plus sine 30 is a half, so 0.5 T2. It's 19.6 newtons. T2 would be 19.6 divided by parentheses 0.726 plus 0.5. And I get 16 newtons. All right, so we still need T1, and we said that T1 is 1.13 T2. So T1 equal to 1.13 T2 is equal to 1.13 times 16 newtons. So 16 times 1.13 gives us 18.1 newtons. All right. 6. A box sits at rest on an incline of 25 degrees. Find the minimum value of the coefficient of static friction between the box and the incline. Okay, this is a nice result that we went over in class. I can recognize immediately that the answer to this is going to be tangent 25 degrees. But we need to show it, right? This is a class in problem solving, not memorizing. So let's show that. Here's my free body diagram. I've got a normal force, friction up the ramp, and gravity towards the earth. Using a tilted coordinate axis, and some are forces. Sum of forces in the y, we get the normal force minus Fg cosine theta equals 0. This is one of those cases where the trig is confusing because you get the cosine in the y. If you just do it looking at the triangles, it makes sense because the y component here is the adjacent side to the angle. In the x direction, we get Fg sine theta minus the friction is equal to 0, right? Because it's sitting at stationary on the ramp. All right, let's see. What other equations do we need? Well, we know that the gravity is mg, and we know that friction is less than or equal to mu times the normal force. Since we're looking for the minimum value of the coefficient of static friction, we can use equality here. Since this is a limiting case, we'll have equality. All right, so we have 4 equations that we're using here, actually. I know this one's kind of trivial. We've used it a lot, but. So we have that the normal force is equal to mg cosine theta after we plug in our gravity. And if we look at our friction equation, we have friction is equal to mu times the normal force. So I'm going to go ahead and plug that in as well, right, using this equation. And now we're going to plug that into our x equation. So plug that into our x equation, and we get the mg sine theta is equal to mu mg cosine theta. We can divide by m and divide by g. We get that mu is equal to sine theta divided by cosine theta, which is the result that we expected, right? Tangent of the angle. Right, so this is the amount of work that would be required though. You would need motion equations, you would need a free body diagram. You can't just say, I know it's tangent of the angle. That goes for the other questions too. All right, 2 boxes are connected by a cord, pulled across a frictionless floor. Mu equal to 0 means frictionless, by a force applied to box B. If F is horizontal and 30 newtons, mass of A is 2 kilograms, mass B is 5 kilograms. Find the acceleration of the boxes and the tension in the cord. So A and T. So let's look at our free body diagrams for both objects. If we look at A, we have mg on A. We have normal force on A, and we have a tension. If we look at B, we have normal force on B, mb times g, tension in the opposite direction because the cord is connecting the 2 blocks, and then the applied force to the right. All right, so there's no motion in the y direction, so let's just look at the x direction. We have t equal to ma times the acceleration. Since there's no friction, I'm not going to do the y direction. For this one, we have F minus T is equal to MB times A. And we can just plug this in for the tension. We get F minus mass A times A equals mass B times A. And the force is equal to the sum of the masses times the acceleration. Oops. And the acceleration then is equal to F over the sum of the masses. Let's see. The force was 30 newtons, and we're dividing by 2 kilograms plus 5 kilograms. 30 over 7 gives us 4.29. All right, if we want to find the tension, we could use either equation. It looks pretty easy to me to use our motion equation for block A, though. Tension is equal to mass A times the acceleration. Mass A is 2 kilograms. So 2 kilograms times 4.29 meters per second squared. Eight 0.57 newtons. And rounding, you may get something different there because I kept everything in the calculator, and you can see that if you rounded it after adding there, you get 5. If you add it after rounding, you get 8.58. That's fine. Number 8. A certain spring stretches 3.5 centimeters when holding a 1 kilogram mass that's hanging from it. Find K. Okay, so that's not too bad. Here's a ceiling, here's a spring, mass hanging on it. So if we do a free body diagram for a mass, we have the force of gravity and the spring force, and it's not touching anything else, so that's it. So the only thing that we need here is the force of gravity is mg. Oh, I've already written mg. And the spring force is kx. And I'm going to absolute value that here. Right. We learned that as minus kx, but we're introducing the directions in our equation, so it doesn't matter. All right, so if we look at our y direction here, we've got the spring force minus mg equals 0 because it's hanging there in equilibrium. So kx is equal to mg, and we're solving for k, mg over x. 1 kilogram, 9.8 newtons per kilogram, and 0.035 meters, right? So I'd say the pitfall on this one is the unit conversion. You may remember when we did this in class with a similar question where we had a car, I left it in centimeters and got an answer that didn't make sense. All right, and I get that my spring constant here is 280 newtons per meter, right? And those are the correct units for a spring constant, right? Each meter that I were to stretch this spring, it would apply 280 newtons. That's correct. All right, 9. A textbook thrown in frustration slides on the floor with an initial velocity. So here's our book sliding across the floor. V naught is 2 meters per second. If the book stops after 1.5 meters, find mu k. Find the kinetic coefficient of friction. All right, so if we're looking for the coefficient of friction, that means that we want the frictional force. And to do that, we're going to need the acceleration. So we need to do the kinematics first. So v squared equals v naught squared plus 2a delta x. That just, when you're given both the initial and final velocities, this tends to be the equation you go to. I realize this sheet, that's the only kinematics I've done on it. I should have mixed up some kinematics, maybe done a projectile problem. Our v final is 0. Our v naught squared is 4. 2a is what we're looking for, and 1.5 meters. So we have minus 4 divided by 2 times 1.5 meters per second squared. Right, that's 4 over 3, 1.33 for our acceleration. All right, but the acceleration isn't what we're looking for, right? What we really want to know is mu. So now we do our free body diagram. Got the force of gravity, normal force, frictional force, and you'll notice this is negative, right? Because the frictional force is in the negative x direction because we're slowing down. And we start out moving in the positive x direction the way I'm drawing. All right, so this just tells us that minus friction equals ma. And it tells us that normal force minus gravity equals 0. Right, that's our sum of forces in the x, sum of forces in the y. So the normal force is equal to mg, and the frictional force we know is equal to mu times the normal force. All right, and we said from our free body diagram that the frictional force is equal to ma. So we get, let me not skip steps, right? So we got friction equal to ma. So we get minus the mu times the normal force equal to ma, minus mu times mg equal to ma. Now we divide by m, and we get mu is equal to minus a over g. A was negative 1.33, so it's 1.33. And our units cancel because it's the ratio of two forces. We already canceled the mass, so it looks like the ratio of two accelerations, but it's really the ratio of two forces. 1.33 divided by 9.8 gives us 0.136 for mu. All right, that was everything on this sheet, so I'm going to leave it there. Remember, this is not inclusive of everything that could be on the test, but if you can do this, you have a vast majority of everything covered.